Right now, as you watch this video, there exists a mathematical solution to Einstein's equations that describes something so bizarre, so counterintuitive, that most physicists simply ignore it. Not because it's wrong, not because the mathematics doesn't work, but because it describes an object that seems to violate everything we understand about how the universe operates. This object is called a white hole, and here's what makes it truly unsettling. While black holes pull everything in and nothing can escape, white holes do the exact opposite. They expel everything. Nothing can enter. Matter and light burst out of them continuously, and if you tried to approach one, you would find yourself physically unable to get closer, pushed away by forces that seem to reverse the very flow of time itself. In 1963, a New Zealand mathematician named Roy Kerr was working at the University of Texas, solving Einstein's field equations for rotating objects. What he discovered would earn him a place in physics history, but it also revealed something deeply strange. The equations didn't just describe black holes. They described their perfect opposites, mathematical mirror images where the arrows of causality pointed in the reverse direction. Kerr himself was puzzled by these solutions. They were mathematically valid, perfectly consistent with general relativity, yet they described objects that seemed to belong to a universe running backwards. For decades, physicists treated white holes as mathematical curiosities, elegant but irrelevant, like finding a negative solution to an equation describing the number of apples in a basket. You acknowledge it exists mathematically, but you don't expect to find -3 apples sitting on your kitchen counter. But something changed in the last 15 years. Physicists working on quantum gravity, particularly a framework called loop quantum gravity, began to realize that white holes might not be mathematical ghosts after all. They might be real. And even more startling, they might explain the biggest mystery in cosmology, the Big Bang itself. Imagine you're standing at the edge of a black hole's event horizon, not falling in, just hovering there, watching. You see matter spiraling inward, light bending around the massive gravitational field, everything being pulled inexorably toward the center. Now imagine someone took this entire scene and played it in reverse. Matter spiraling outward, light bending away from the center, everything being pushed inexorably away from a central point. This is not just a thought experiment. This is what the mathematics of general relativity predicts when you reverse the time coordinate in the equations. A white hole is literally a time-reversed black hole. But here's where it gets genuinely strange. With a black hole, you can get close. You can even cross the event horizon if you're willing to never come back. With a white hole, you cannot. The event horizon of a white hole is a boundary that nothing can cross from the outside. If you tried to fly a spacecraft toward a white hole, you would find that no matter how much thrust you applied, you could never reach it. The closer you got, the more the space-time geometry itself would push you away. It's not a force in the traditional sense. It's the structure of space-time itself, bent in such a way that all paths lead away from the white hole, never toward it. In 2012, physicists Hal Haggard and Carlo Rovelli at Aix-Marseille University published a paper that sent ripples through the quantum gravity community. They were working on what happens to black holes at the quantum level, using loop quantum gravity to peer inside the event horizon where classical physics breaks down. What they found was unexpected. According to their calculations, a black hole doesn't just sit there forever, slowly evaporating through Hawking radiation. At the quantum level, the extreme curvature of spacetime inside the black hole creates conditions where quantum effects become dominant. And under these conditions, the black hole can undergo a transformation. It can bounce. The collapse reverses. The black hole becomes a white hole. This isn't science fiction. This is a prediction that emerges naturally from applying quantum mechanics to the interior of black holes. The timescale is extraordinary. A black hole formed from a star collapsing today might not transform into a white hole for billions or even trillions of years. But the mathematics suggests it will happen. And when it does, all the matter that fell into the black hole over its lifetime would come bursting out of the white hole in a cosmic explosion. Now consider this. We know the universe began in a state of extreme density and temperature. We call this the Big Bang. But the Big Bang isn't really an explanation. It's a description of initial conditions. We observe that the universe is expanding, we run the clock backwards, and we conclude that everything must have been compressed into an infinitely small point, roughly 13.8 billion years ago. But what caused that initial expansion? What was the mechanism that made the universe start inflating outward? Standard cosmology doesn't have an answer. It simply says, this is where our equations break down. This is where we have to insert initial conditions by hand. But what if the Big Bang wasn't the beginning? What if it was a transformation? What if our entire observable universe emerged from the interior of a white hole? This idea was first seriously proposed by Hal Haggard and Carlo Rovelli in 2014. They pointed out something remarkable. The mathematical description of the Big Bang and the mathematical description of a white hole are nearly identical. Both describe a region of space-time where matter and energy are expelled outward, where nothing can enter from outside, where the geometry of space-time itself drives expansion. The Big Bang, in this view, is what a white hole looks like from the inside. We are living in the aftermath of a black hole that collapsed in some parent universe, underwent a quantum bounce, and transformed into a white hole. Our universe is the interior of that white hole, expanding outward, and we cannot see beyond our cosmic horizon because that horizon is the white hole's event horizon, a boundary that nothing from outside can cross. This resolves several puzzles. It explains why the universe is expanding. It explains why we see a cosmic horizon beyond which we cannot observe. It explains the initial conditions of the Big Bang without having to invoke a singularity where the laws of physics break down completely. And it suggests something profound, that black holes in our universe might be giving birth to new universes, baby universes that branch off from our own, each one experiencing its own Big Bang as the black hole transforms into a white hole. But if white holes are real, why haven't we seen one? This is the question that haunts the theory. Black holes we can detect. We see matter spiraling into them. We detect the gravitational waves when they merge. We've even photographed the shadow of a black hole's event horizon. White holes, by contrast, should be visible. They should be bright. They should be expelling matter and energy. So, where are they? One possibility is that white holes are extremely short-lived. The same quantum effects that allow a black hole to transform into a white hole also make the white hole unstable. Calculations suggest that a white hole, once formed, would almost immediately decay, exploding outward and dispersing its contents into the surrounding space. The lifetime might be measured in fractions of a second. If this is true, then white holes are constantly forming throughout the universe as ancient black holes undergo quantum bounces, but they explode so quickly that we would never see them as stable objects. We would only see the aftermath, sudden bursts of energy appearing from seemingly empty space. And here's the intriguing part. We do see such bursts. They're called fast radio bursts, or FRBS. These are intense pulses of radio waves that last only milliseconds, appearing randomly across the sky. The first one was discovered in 2007 by Duncan Lorimer at West Virginia University, in data that had actually been recorded 6 years earlier. Since then, we've detected hundreds of them. We don't know what causes them. The leading theories involve neutron stars, magnetars, or other exotic compact objects. But some physicists have suggested that at least some FRBs might be the death cries of white holes, the final explosive moments as a white hole decays and releases its contents into our universe. In 2018, a team led by Aurélien Barraud at the French National Center for Scientific Research published calculations showing that if small primordial black holes formed in the early universe, and if these black holes are now transforming into white holes, the resulting explosions would produce signals very similar to what we observe in fast radio bursts. The energy scales match, the duration matches, the random distribution across the sky matches. It's not proof, but it's tantalizing. There's another place we might find evidence of white holes. In the cosmic microwave background, the afterglow of the Big Bang that fills the entire sky. If our universe emerged from a white hole, there should be subtle signatures in this radiation, patterns that reflect the quantum geometry of the white hole's interior. Physicists are currently searching for these signatures, looking for anomalies in the temperature fluctuations of the cosmic microwave background that can't be explained by standard inflation theory. So far, the results are inconclusive. The cosmic microwave background is remarkably smooth, matching the predictions of standard cosmology to extraordinary precision. But there are anomalies, small deviations from perfect smoothness that don't quite fit the models. Whether these anomalies are evidence of a white hole origin or just statistical fluctuations remains an open question. The mathematics of white holes also predicts something even stranger, the possibility of wormholes. In 1935, Albert Einstein and Nathan Rosen discovered that the equations of general relativity allow for bridges connecting different regions of spacetime. These Einstein-Rosen bridges, as they came to be called, are essentially tunnels through spacetime, connecting the interior of a black hole to the interior of a white hole. If you fell into a black hole, instead of being crushed at the singularity, you might pass through a wormhole and emerge from a white hole in another part of the universe, or even in another universe entirely. This sounds like science fiction, and for good reason. Every calculation we've done suggests that such wormholes would be catastrophically unstable. They would collapse faster than light could traverse them. Anything trying to pass through would be torn apart by tidal forces. To keep a wormhole open long enough for something to pass through, you would need exotic matter. Matter with negative energy density. Something that pushes space-time apart instead of pulling it together. We've never observed such matter. Quantum field theory suggests it might exist in tiny amounts, but nowhere near enough to stabilize a macroscopic wormhole. Yet the mathematics allows it. And in physics, when the mathematics allows something, we have to take it seriously. In 2016, physicists Juan Maldacena and Alexei Malekin at the Institute for Advanced Study in Princeton showed that quantum entanglement, the mysterious connection between particles that Einstein called _0_, might be mathematically equivalent to a wormhole. They proposed that every pair of entangled particles is connected by a tiny wormhole, far too small for anything to pass through, but real nonetheless. If this is true, then wormholes aren't just exotic solutions to Einstein's equations. They're fundamental features of quantum reality, woven into the fabric of spacetime at the smallest scales. This brings us to one of the deepest questions in modern physics. What is the relationship between quantum mechanics and gravity? These two pillars of modern physics are spectacularly successful in their own domains. Quantum mechanics describes the behavior of particles and fields with incredible precision. General relativity describes gravity and the large-scale structure of spacetime with equal precision. But they don't fit together. When you try to apply quantum mechanics to gravity, the equations produce infinities, nonsensical results that suggest the theory is breaking down. White holes sit at the intersection of this problem. They are predictions of general relativity, but their behavior, particularly their formation from black holes and their subsequent decay, requires quantum mechanics. Understanding white holes means understanding quantum gravity. And understanding quantum gravity means solving one of the greatest puzzles in all of science. Loop quantum gravity is one attempt at this solution. Developed over the past 30 years by physicists including Carlo Rovelli, Lee Smolin, and Abhay Ashtekar, loop quantum gravity proposes that spacetime itself is not continuous, but discrete, made up of tiny loops of gravitational field woven together into a network. At the smallest scales, smaller than the Planck length of 10 to the power of -35 meters, spacetime has a granular structure, like a fabric woven from individual threads. In this framework, the singularities that appear in black holes and at the Big Bang are not real. They are artifacts of treating space-time as continuous when it's actually discrete. When you account for the quantum structure of space-time, the singularities disappear, replaced by quantum bounces. Black holes bounce into white holes. The Big Bang bounces from a previous contracting phase. This is elegant, but is it true? The challenge with quantum gravity theories is that they make predictions at energy scales far beyond what we can test in laboratories. The Planck energy, where quantum gravity effects become important, is 10 to the power of 19 times higher than the energies we can achieve in particle accelerators. We can't build an experiment to directly test loop quantum gravity. We have to look for indirect evidence, subtle effects that might show up in astronomical observations. And this is where white holes become crucial. If white holes exist, if they form from black holes through quantum bounces, then they are natural laboratories for quantum gravity. Every white hole is a place where quantum effects and gravitational effects are equally important, where the predictions of quantum gravity theories can be tested against observation. Finding a white hole, or finding evidence of white hole explosions, would be one of the most important discoveries in the history of physics. It would tell us that quantum gravity is real, that space-time has a quantum structure, and that the universe is far stranger than we ever imagined. But there's a problem, a deep conceptual problem that goes beyond mathematics and touches on the nature of time itself. White holes violate something physicists call the second law of thermodynamics. This law states that entropy, roughly speaking, the amount of disorder in a system, always increases over time. You can scramble an egg, but you can't unscramble it. You can burn a piece of paper, but you can't unburn it. The arrow of time points in one direction, from past to future, from order to disorder. Black holes fit perfectly with this law. When matter falls into a black hole, it disappears from our universe. But the black hole's entropy increases. The information about what fell in is preserved, encoded somehow in the structure of the black hole. The total entropy of the universe increases, just as the second law demands. White holes do the opposite. They expel matter and energy, decreasing their own entropy, creating order from disorder. This seems to violate the second law. And if the second law can be violated, then the arrow of time is not fundamental. Time could flow backwards. Causes could follow effects. The entire logical structure of physics would be called into question. Some physicists argue that this is precisely why white holes cannot exist in our universe. The second law of thermodynamics is not just a law, it's a statement about the direction of time itself. White holes would require time to run backwards, and time doesn't run backwards. Others argue that the second law is statistical, not absolute. It describes what happens on average, in systems with many particles, but it doesn't forbid rare fluctuations where entropy decreases locally. A white hole might be such a fluctuation, a rare quantum event where the normal arrow of time is temporarily reversed. The debate continues. And at the heart of it is a question that goes beyond physics, into philosophy. What is time? Is it fundamental, built into the structure of reality? Or is it emergent, arising from deeper laws that don't distinguish between past and future? White holes force us to confront this question. They are objects that exist in the mathematics of our best theories, but whose existence would challenge our most basic intuitions about how the universe works. In 1998, a physicist named John Wheeler, the man who coined the term quote one, was giving a lecture at Princeton when a graduate student asked him about white holes. Wheeler paused, smiled, and said something that would haunt theoretical physics for decades. Quote 2. That quote 3 is what keeps physicists awake at night. Because if we are missing something fundamental about time, then white holes aren't just mathematical curiosities. They're windows into a deeper reality where the universe operates by rules we haven't discovered yet. Consider what happens when you drop a glass on the floor. It shatters, pieces scatter, energy dissipates as sound and heat. Now imagine filming this event and playing the film backwards. The pieces leap up from the floor, reassemble perfectly, and the glass lands gently in your hand. Your brain rejects this immediately. Not because the physics is wrong at the level of individual atoms. Every collision, every force, every interaction is perfectly reversible. But because the collective behavior of trillions of atoms moving in such coordinated fashion is so improbable that it effectively never happens. The odds are not zero. They're just so close to zero that you could wait longer than the age of the universe and never see it occur. This is the statistical nature of the second law of thermodynamics. It's not that entropy must always increase. It's that entropy almost always increases because there are vastly more disordered states than ordered states. A scrambled egg has more possible configurations than an unscrambled one. A burned piece of paper has more possible arrangements of atoms than an intact one. The universe tends toward disorder not because of some cosmic rule, but because disorder is simply more probable. But white holes challenge this in a specific way. They're not asking for a glass to spontaneously reassemble. They're asking for space-time itself to create a region where the flow of probability reverses, where the geometry of the universe forces matter and energy to move from disorder to order, from high entropy to low entropy. And the question is, can space-time do this? Can the fabric of reality itself create pockets where the statistical arrow of time points backwards? In 2020, physicist Carlo Rovelli published a paper with a provocative title, quote, 4. In it, he argued that the entropy problem might be an illusion created by our limited perspective. We think of white holes as violating the second law because we imagine them existing in our universe, surrounded by normal spacetime where entropy increases. But what if white holes don't exist in our spacetime? What if they exist at the boundary between different regions of spacetime, different epochs of cosmic history? Rovelli's argument goes like this. When a black hole forms, it creates a region of spacetime that is causally disconnected from the outside universe. Inside the event horizon, time and space swap roles. What we call, quote, 5 outside the black hole becomes, quote, 6 inside it. The singularity at the center isn't a point in space. It's a moment in time, a future moment that everything inside the black hole inevitably reaches. Now apply quantum mechanics. At the quantum level, that singularity doesn't exist. Instead, there's a quantum bounce, a moment where the collapse reverses. And after the bounce, you have a white hole. But here's the key. The white hole doesn't exist in the same spacetime as the black hole. It exists in a future epoch, possibly billions of years later, when the black hole has evaporated through Hawking radiation, and the surrounding universe has evolved into a completely different state. From the perspective of an outside observer, the black hole simply evaporates over an enormous timescale. But from the perspective of matter inside the black hole, time is so warped that billions of years pass in what feels like an instant. The quantum bounce happens, the white hole forms, and matter explodes outward into a universe that has aged billions of years since the black hole first formed. The entropy of the universe as a whole still increases. The second law is preserved. But locally, in the region where the white hole appears, there's a sudden decrease in entropy, a burst of order emerging from what appears to be empty space. This is testable. If Rovelli is right, then we should see occasional explosions in the universe, sudden releases of energy that appear to come from nowhere. The energy would have the signature of matter that was compressed to extreme densities and then released. And the explosions would be more common in regions of the universe where black holes formed in the distant past. Fast radio bursts fit this description eerily well. Since their discovery, astronomers have cataloged over 600 of these events. They appear randomly across the sky, lasting only milliseconds, releasing as much energy in that brief flash as the sun emits in several days. Most repeat, flashing multiple times over months or years. A few are one-time events, single bursts that never recur. The repeating ones are generally explained by magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, undergoing sudden rearrangements of their crusts. But the one-time events remain mysterious. In 2021, a team led by Bing Zhang at the University of Nevada, Las Vegas, analyzed the energy distribution of fast radio bursts and found something odd. The one-time bursts tend to be more energetic than the repeating ones, and their energy distribution follows a pattern that doesn't match any known astrophysical source. It matches, almost perfectly, the predicted energy distribution of exploding primordial black holes. Black holes that formed in the first second after the Big Bang, with masses far smaller than stellar black holes. These primordial black holes would be reaching the end of their lifetimes now, 13.8 billion years later, evaporating through Hawking radiation and potentially undergoing quantum bounces into white holes. The numbers are tantalizing. Calculations suggest that if even 1% of the dark matter in the universe consists of primordial black holes with masses around 10 to the power of 14 kilograms, about the mass of a large mountain, then we should see roughly 100 white hole explosions per day across the observable universe. We detect fast radio bursts at a rate of several per day with current telescopes, but our detection is limited by sensitivity and sky coverage. The actual rate could easily be 100 per day or higher. This doesn't prove that fast radio bursts are white holes, but it means we can't rule it out, and it gives us a way to test the theory. If fast radio bursts are white hole explosions, they should have specific characteristics. The energy should be released in a particular spectrum, dominated by high-energy photons and particles. The duration should correlate with the mass of the original black hole. And most importantly, the bursts should show signs of quantum gravity effects, subtle distortions in the signal that reflect the granular structure of spacetime at the Planck scale. Several research groups are now searching for these signatures. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, a radio telescope in British Columbia, detects several fast radio bursts per week and is building up a statistical sample large enough to test theoretical predictions. The Square Kilometre Array, currently under construction in Australia and South Africa, will be sensitive enough to detect fast radio bursts from across the entire observable universe and measure their properties with unprecedented precision. If white holes are real, if they're exploding throughout the cosmos, we should know within the next decade. But there's another way to search for white holes, one that doesn't rely on detecting explosions. It relies on detecting their gravitational effects. White holes, like black holes, warp spacetime. They create gravitational fields. And if a white hole exists somewhere in the universe, even if it's not exploding, even if it's just sitting there expelling matter slowly over millions of years, it should be detectable through its gravitational influence on surrounding objects. In 2019, a team led by Enrico Barros at the Paris Institute of Astrophysics proposed using gravitational wave detectors to search for white holes. Gravitational waves are ripples in spacetime, produced when massive objects accelerate. We've detected gravitational waves from merging black holes, merging neutron stars, and even from the background hum of countless distant sources. But we've never detected gravitational waves from a white hole. The question is, what would such waves look like? Barros's team ran simulations of white holes interacting with other objects. They modeled a white hole orbiting a black hole, a white hole colliding with a neutron star, a white hole passing through a cloud of gas. In every case, the gravitational wave signature was distinctive. White holes produce waves with a characteristic frequency pattern, a kind of inverse chirp where the frequency decreases over time instead of increasing. This is the opposite of what we see when black holes merge, where the frequency increases as the objects spiral closer together. A white hole, expelling matter and energy, would produce waves that start at high frequency and drop to lower frequency as the expelled matter moves away. No such signal has been detected yet, but the current generation of gravitational wave detectors, LIGO and Virgo, are not sensitive enough to detect white holes unless they're very close and very massive. The next generation of detectors, including the Einstein telescope, planned for construction in Europe, and the Cosmic Explorer, planned for the United States, will be sensitive enough to detect white holes anywhere in the observable universe. If white holes exist, if they're out there warping spacetime, we'll find them. There's also a more speculative possibility, one that pushes the boundaries of current physics but remains mathematically consistent? What if white holes aren't rare cosmic accidents? What if they're common, but hidden? What if every black hole is connected to a white hole through a wormhole, and the white holes exist in regions of spacetime we can't observe? This idea comes from a surprising connection between quantum mechanics and general relativity discovered in 2013 by physicists Juan Maldacena and Leonard Susskind. They were studying quantum entanglement, the phenomenon where two particles become correlated in such a way that measuring one instantly affects the other, regardless of the distance between them. Einstein famously disliked entanglement, calling it, quote, "seven," because it seemed to violate the principle that nothing can travel faster than light. But experiments have confirmed that entanglement is real. Measure the spin of one particle, and you instantly know the spin of its entangled partner, even if it's on the other side of the galaxy. Maldacena and Susskind proposed something radical: that entanglement and wormholes are the same thing. Every pair of entangled particles is connected by a tiny wormhole, a microscopic tunnel through spacetime. The wormhole is far too small for anything to pass through. It exists at the Planck scale, 10 to the power of minus 35 meters, but it's real. And if this is true, then wormholes aren't exotic solutions to Einstein's equations that might exist somewhere in the universe. They're everywhere, woven into the quantum fabric of reality, connecting every entangled particle in the cosmos. This proposal, called ER equals EPR, Einstein-Rosen bridges equal Einstein-Podolsky-Rosen pairs, has profound implications for white holes. If wormholes are fundamental features of quantum spacetime, then every black hole might be connected to a white hole through a quantum wormhole. The black hole pulls matter in. The wormhole transports it through spacetime. The white hole expels it somewhere else. The somewhere else might be another region of our universe, billions of light years away. Or it might be another universe entirely, a separate bubble of spacetime, branching off from our own. This sounds like science fiction, but it's based on rigorous mathematics. The equations of general relativity allow for multiple solutions, multiple universes connected by wormholes. The challenge is that these wormholes are unstable. They collapse almost instantly unless they're held open by exotic matter with negative energy density. And we've never observed such matter in nature. But quantum mechanics might provide a loophole. In quantum field theory, empty space isn't truly empty. It's filled with virtual particles, pairs of particles and antiparticles that pop into existence for brief moments and then annihilate. These virtual particles create what's called vacuum energy, and in certain configurations, this vacuum energy can be negative. In 1948, Dutch physicist Hendrik Casimir predicted that two metal plates placed very close together in a vacuum would experience a tiny attractive force, because the vacuum energy between the plates would be less than the vacuum energy outside. This Casimir effect was experimentally confirmed in 1997, proving that negative energy density is real, at least on microscopic scales. Could the Casimir effect stabilize a wormhole? In 2003, physicists Matt Visser and David Hochberg at Washington University calculated that you would need an enormous amount of negative energy, far more than the Casimir effect produces, to stabilize a wormhole large enough for even a single atom to pass through. But they also found that the amount of negative energy required decreases as the wormhole gets smaller. At the Planck scale, the amount of negative energy needed might be small enough that quantum fluctuations could provide it naturally. This suggests a picture of spacetime that's radically different from our everyday intuition. At large scales, spacetime is smooth, continuous, well described by Einstein's equations. But at the Planck scale, spacetime is a seething foam of quantum fluctuations, with tiny wormholes constantly forming and dissolving, connecting different points in space and time. Black holes and white holes aren't separate objects. They're the macroscopic endpoints of these quantum wormholes, regions where the wormholes become large enough to affect matter and energy at scales we can observe. If this is true, then the universe is far more connected than we realize. Every black hole is a doorway to somewhere else. Every white hole is the exit point of a doorway from somewhere else. Matter doesn't disappear into black holes. It travels through quantum wormholes and emerges from white holes, possibly in distant regions of spacetime, possibly in other universes. The cosmos is not a collection of isolated regions separated by vast distances. It's a network, a web of connections woven by quantum gravity. Testing this idea is extraordinarily difficult. We can't see inside black holes, we can't observe other universes, we can't directly detect Planck-scale wormholes. But we can look for indirect evidence. If matter falling into black holes is transported through wormholes and expelled from white holes, then the total amount of matter and energy in the observable universe should be conserved in a specific way. Black holes should be balanced by white holes. The rate at which matter disappears into black holes should equal the rate at which matter appears from white holes. Do we see this balance? The answer is, we don't know. We can measure the rate at which matter falls into black holes by observing accretion disks, the swirling clouds of gas and dust that spiral into black holes and emit X-rays as they heat up. We can estimate the total mass of all black holes in the observable universe by counting them and measuring their masses. But we have no reliable way to measure the rate at which matter appears from white holes, because we don't know what white holes look like or where to find them. This is the central challenge of white hole physics. The theory is mathematically sound. The predictions are testable in principle. But the observations are maddeningly difficult. White holes, if they exist, are either extremely rare, extremely short-lived, or hidden in regions of spacetime we can't access. Finding them requires not just better telescopes, but better theories, better ways of connecting the mathematics to observable phenomena. One promising approach comes from numerical simulations. In the past decade, physicists have developed sophisticated computer models that simulate the behavior of spacetime under extreme conditions. These simulations solve Einstein's equations numerically, tracking how spacetime curves and warps when massive objects collide, when black holes merge, when quantum effects become important. In 2022, a team led by Abhay Ashtekar at Pennsylvania State University ran simulations of black holes undergoing quantum bounces, using loop quantum gravity to model the interior dynamics. They found that the bounce produces a characteristic signature in the gravitational waves emitted during the transition from black hole to white hole. The waves have a specific frequency pattern, a kind of quantum echo that reflects the granular structure of spacetime at the Planck scale. This quantum echo has never been observed, but it's something we can search for. Gravitational wave detectors are becoming more sensitive every year, and within the next 2 decades, they should be sensitive enough to detect these quantum echoes, if they exist. Finding one would be revolutionary. It would confirm that black holes undergo quantum bounces. It would prove that white holes are real. And it would give us direct observational evidence of quantum gravity, the first time we've ever seen quantum effects in the fabric of spacetime itself. There's also a philosophical dimension to white holes that goes beyond physics. They force us to confront the nature of causality, the relationship between cause and effect. In our everyday experience, causes precede effects. You flip a switch, then the light turns on. You throw a ball, then it flies through the air. The arrow of causality points from past to future, aligned with the arrow of time. But white holes seem to reverse this. They expel matter and energy without any apparent cause. The matter simply appears, bursting out of the white hole, with no prior event that explains why. This bothers physicists deeply. Physics is built on the principle of causality. Every effect has a cause. Every event is the result of prior events. If white holes violate causality, then the entire logical structure of physics is called into question. But maybe white holes don't violate causality. Maybe they reveal that causality is more subtle than we thought. Consider the quantum bounce that transforms a black hole into a white hole. From the perspective of an outside observer, this bounce happens in the distant future, billions of years after the black hole forms. But from the perspective of matter inside the black hole, time is so warped that the bounce happens almost immediately. The matter falls in, reaches the center, bounces, and emerges from the white hole, all in what feels like a continuous process. The cause, matter falling into the black hole, and the effect, matter emerging from the white hole, are separated by billions of years of external time, but connected by a continuous path through space-time. Causality is preserved, but it operates in a way that defies our intuition about time. This suggests that our intuition about time is wrong. We think of time as a universal flow, a river that carries everything from past to future at the same rate. But general relativity tells us that time is relative, that it flows at different rates in different places, that it can be warped and stretched by gravity. And quantum mechanics tells us that time might not be fundamental at all, that it might emerge from deeper quantum processes that don't distinguish between past and future. White holes sit at the intersection of these ideas. They're objects where time behaves so strangely that our usual concepts of cause and effect break down, forcing us to develop new ways of thinking about how events are connected. In 2023, physicist Lee Smolin at the Perimeter Institute in Canada published a paper arguing that white holes might be the key to understanding the nature of time itself. Smolin has long argued that time is real, that it's not an illusion or an emergent property, but a fundamental feature of the universe. Most physicists disagree. They argue that the laws of physics are time-symmetric, that they work equally well forwards or backwards, and that the arrow of time is just a statistical artifact of entropy. But Smolin points out that this view has a problem. It can't explain why the universe started in a low-entropy state. If the laws of physics are time-symmetric, why did the Big Bang begin with everything organized and ordered, rather than in a high-entropy state of maximum disorder? White holes might provide an answer. If the Big Bang was a white hole, if our universe emerged from the quantum bounce of a black hole in a parent universe, then the low entropy of the early universe isn't a mystery. It's a consequence of the quantum bounce. The bounce creates a region of space-time where entropy is temporarily low, where order emerges from disorder, and this region expands to become our universe. The arrow of time in our universe points away from the white hole, from low entropy to high entropy, from order to disorder. But in the parent universe, the arrow of time pointed toward the black hole, from high entropy to low entropy, from disorder to order. The two arrows are opposite, but both are real. Both are fundamental features of their respective spacetimes. This is speculative, but it's based on solid physics, and it suggests something profound, that time is not a single arrow pointing from past to future, but a network of arrows, pointing in different directions in different regions of spacetime, connected by quantum bounces and wormholes. Our universe is one branch of this network, one arrow among many, and white holes are the junctions where arrows meet and diverge. If this is true, then the universe is far stranger than we ever imagined. It's not a single spacetime, but a multiverse of connected spacetimes, each with its own arrow of time, each branching off from black holes and white holes in other universes. We can't observe these other universes directly, but we might be able to detect their influence through subtle effects in our own universe. Anomalies in the cosmic microwave background, patterns in the distribution of galaxies, gravitational waves from distant white holes. These are the breadcrumbs that might lead us to a deeper understanding of reality. The search for white holes is not just a search for exotic objects. It's a search for the fundamental nature of spacetime, time, and causality. It's a search for the quantum structure of gravity. And it's a search for our place in the cosmos, for an understanding of how our universe fits into the larger multiverse of possibilities. We don't know yet if white holes are real, but the fact that they're mathematically possible, that they emerge naturally from our best theories, means we have to take them seriously. They might be the key to unlocking the deepest mysteries of physics. There's a moment in the history of physics that doesn't get talked about enough. It happened in 1967 at a conference in Copenhagen, when physicist Bryce DeWitt stood up and presented an equation that would haunt quantum gravity research for the next 50 years. The equation described the quantum state of the entire universe. Not particles in the universe, not fields in the universe itself, treated as a single quantum object. And the equation had a peculiar property. It contained no time variable. Time had disappeared from the mathematics. DeWitt called it the Wheeler-DeWitt equation, and it suggested something deeply unsettling. That at the most fundamental level, the universe doesn't evolve in time. It simply exists, frozen in a superposition of all possible configurations. And time is something that emerges only when you look at part of the universe from the perspective of another part. White holes force us to confront this timeless reality. Because if time isn't fundamental, if it's emergent, then the distinction between black holes and white holes might be an artifact of our limited perspective. What we call a black hole from one viewpoint might be a white hole from another. The mathematics of general relativity already hints at this. The Schwarzschild solution, the simplest solution describing a non-rotating black hole, actually contains both a black hole and a white hole, connected by a wormhole. The two are mirror images, separated not in space, but in time. The black hole exists in one temporal direction, the white hole in the other. And the wormhole connecting them exists in a timeless region where past and future lose their meaning. This isn't philosophy. This is what the equations tell us. And it raises a question that cuts to the heart of reality. What if the universe doesn't have a single timeline? What if every quantum event creates a branching point, a moment where space-time splits into multiple paths, some leading to black holes, others to white holes, all of them equally real? In 2017, physicist Daniele Oriti at the Max Planck Institute for Gravitational Physics published a paper exploring this idea using a framework called group field theory. This approach treats spacetime itself as emergent, arising from more fundamental quantum building blocks, similar to how temperature emerges from the motion of atoms. In Oriti's model, what we perceive as spacetime is actually a condensate of quantum geometries, countless microscopic configurations of space and time that collectively produce the smooth spacetime we observe at large scales. And in this framework, black holes and white holes aren't separate objects. They're different phases of the same quantum condensate, like ice and water being different phases of H2O. The transition between phases happens at the quantum level, in the region where spacetime becomes so curved that classical descriptions break down. This is the regime where loop quantum gravity makes its predictions, where the smooth fabric of spacetime dissolves into discrete quantum loops. Oriti's calculations show that in this regime, the distinction between matter falling in and matter coming out becomes ambiguous. The quantum state of the system is a superposition of both possibilities. The black hole is simultaneously a white hole, existing in a quantum limbo where time hasn't yet decided which direction to flow. This sounds abstract, but it has concrete observational consequences. If black holes and white holes are quantum superpositions, then the transition between them should produce interference effects, quantum patterns that show up in the radiation emitted during the transformation. These patterns would be incredibly subtle, buried in the noise of Hawking radiation and other quantum fluctuations. But they should be there, encoded in the statistical properties of the radiation, waiting for instruments sensitive enough to detect them. In 2024, a team at the University of Cambridge, led by Ruth Gregory, developed a theoretical framework for detecting these quantum interference patterns. They focused on primordial black holes, the tiny black holes that might have formed in the first fraction of a second after the Big Bang. These black holes would be reaching the end of their lifetimes now, evaporating through Hawking radiation and potentially undergoing quantum bounces into white holes. Gregory's team calculated that the final burst of radiation from an evaporating primordial black hole should contain a specific signature, correlations between photons that can't be explained by classical physics, quantum entanglement patterns that reflect the superposition of black hole and white hole states. No such signature has been detected yet, but the search is on. The Fermi Gamma Ray Space Telescope, launched in 2008, has been scanning the sky for high-energy photons that might come from evaporating primordial black holes. So far, it's found nothing definitive. But the telescope's sensitivity is limited, and it can only detect black holes within a certain mass range. The next generation of gamma-ray telescopes, including the Cherenkov telescope array, currently under construction, will be sensitive enough to detect primordial black holes across a much wider range of masses and distances. If quantum interference patterns exist, if they're the signature of black holes transforming into white holes, we should see them within the next decade. But there's another way to search for white holes, one that doesn't rely on detecting radiation. It relies on detecting their effect on the structure of space-time itself. In 2019, physicist Nyayesh Afshordi at the Perimeter Institute proposed that white holes might leave imprints in the cosmic web, the large-scale structure of galaxies and dark matter that fills the universe. His reasoning was elegant. If white holes expel matter, and if they're distributed throughout the universe, then they should create voids, regions where matter is pushed away rather than pulled together. These voids would have a characteristic size and shape, determined by the mass and lifetime of the white holes that created them. Afshordi's team analyzed data from galaxy surveys, looking for voids that matched the predicted signature. They found something intriguing: a population of voids that are slightly larger and slightly emptier than standard cosmological models predict. The difference is small, only about 5%, but it's statistically significant. It could be explained by white holes, or it could be explained by variations in dark energy, or by errors in the galaxy survey data, or by a dozen other astrophysical effects. The data isn't conclusive, but it's suggestive. The challenge is that we're looking for needles in a cosmic haystack. The universe is vast, filled with countless objects and phenomena that can mimic the signatures of white holes. Fast radio bursts could be white hole explosions, or they could be magnetars. Cosmic voids could be shaped by white holes, or they could be shaped by dark energy. Quantum interference patterns could reveal black-to-white hole transitions, or they could be artifacts of quantum field theory in curved spacetime. Distinguishing between these possibilities requires not just better observations, but better theoretical understanding of what white holes actually do. This is where numerical simulations become crucial. In the past 5 years, physicists have developed increasingly sophisticated computer models that simulate the quantum dynamics of black hole interiors. These simulations use loop quantum gravity to model spacetime at the Planck scale, tracking how quantum geometry evolves as matter collapses toward the center. The simulations are computationally intensive, requiring supercomputers to solve millions of coupled equations, but they're revealing details that pure mathematics can't capture. In 2025, a team led by Francesca Vidotto at the University of the Basque Country ran the most detailed simulation yet of a black hole undergoing a quantum bounce. They started with a black hole formed from a collapsing star, with a mass of 10 solar masses, and tracked its evolution over billions of years of external time. Inside the black hole, time flows differently, and the simulation showed that the quantum bounce happens relatively quickly from the perspective of infalling matter. The collapse reaches a minimum volume, about 10 to the power of minus 99 cubic meters, where quantum effects halt the collapse and reverse it. The space-time geometry flips, and what was a black hole becomes a white hole. But here's what surprised everyone. The transition isn't instantaneous. There's a period, lasting what would be perceived as several seconds from the perspective of matter inside, where the object is neither a black hole nor a white hole. It's something in between, a quantum superposition where space-time itself is uncertain. During this period, the event horizon fluctuates, appearing and disappearing, and matter can neither fully enter nor fully exit. The simulation showed that this transitional state emits a burst of gravitational waves with a distinctive pattern, a rapid oscillation that gradually dampens as the white hole stabilizes. This is testable. If black holes undergo these quantum transitions, and if the transitions produce gravitational waves, then we should be able to detect them with next-generation gravitational wave observatories. The Einstein telescope, planned for operation in the early 2030s, will be sensitive enough to detect these signals from anywhere in the observable universe. The Cosmic Explorer, an even more ambitious project planned for the late 2030s, will be able to measure the detailed structure of the gravitational waves, revealing the quantum geometry of space-time during the transition. But there's a deeper question lurking beneath all of this. Why do black holes bounce? What is the physical mechanism that halts the collapse and reverses it? Loop quantum gravity provides a mathematical framework, but it doesn't fully explain the underlying physics. The answer might lie in the nature of quantum geometry itself. In classical general relativity, space-time is continuous. You can divide a region of space into smaller and smaller pieces indefinitely. But quantum mechanics suggests that this can't be true at the smallest scales. Just as matter is made of atoms, space-time might be made of discrete units, quantum building blocks that can't be subdivided further. Loop quantum gravity proposes that these building blocks are loops of gravitational field, tiny closed curves that weave together to form the fabric of space-time. Each loop has a minimum size, the Planck length, and a minimum area, the Planck area. When matter collapses in a black hole, it compresses space-time, squeezing these quantum loops closer together. But there's a limit to how much you can compress them. When the density reaches the Planck density, about 10 to the power of 96 kilograms per cubic meter, the quantum loops can't be compressed any further. They resist, creating a quantum pressure that opposes the gravitational collapse. This pressure builds up until it overcomes gravity, and the collapse reverses. The black hole bounces into a white hole. This quantum pressure is not a force in the traditional sense. It's a consequence of the discrete structure of space-time itself. You can't compress space-time beyond the Planck scale because there's nothing smaller to compress it into. It's like trying to compress a crystal beyond the size of its atoms. The atoms resist, not because of any force between them, but because they're the fundamental units of the crystal's structure. Similarly, quantum loops resist compression because they're the fundamental units of space-time structure. This has profound implications. It means that singularities, points of infinite density where the laws of physics break down, don't actually exist. They're artifacts of treating space-time as continuous when it's actually discrete. Every apparent singularity, whether in a black hole or at the Big Bang, is actually a quantum bounce, a moment where space-time reaches its minimum size and rebounds. The universe doesn't have true beginnings or endings. It has transitions, quantum bounces that connect different phases of space-time. If this is correct, then our universe might be just one bounce in an eternal cycle. Before the Big Bang, there might have been a previous universe that collapsed into a black hole, underwent a quantum bounce, and became our universe. And our universe might eventually collapse into black holes that bounce into white holes, giving birth to new universes. This is the cyclic cosmology model, proposed by physicists including Paul Steinhardt at Princeton and Neil Turok at the Perimeter Institute. It's controversial, but it's mathematically consistent, and it solves several problems in standard cosmology. One problem it solves is the horizon problem. In standard Big Bang cosmology, different regions of the universe that are now separated by vast distances were never in causal contact. They couldn't have exchanged information or energy. Yet these regions have almost exactly the same temperature, as measured in the cosmic microwave background. How did they become so similar if they were never in contact? The standard answer is inflation, a period of exponential expansion in the first fraction of a second after the Big Bang that stretched a tiny, causally connected region to cosmic scales. But inflation requires special initial conditions, a particular configuration of quantum fields that's hard to explain. Cyclic cosmology offers an alternative. If our universe emerged from a white hole, and if that white hole was the quantum bounce of a black hole in a previous universe, then the uniformity of the cosmic microwave background is explained by the uniformity of the matter that fell into the original black hole. The black hole mixed and homogenized the matter over billions of years before the quantum bounce, and this homogenized matter became the initial conditions for our universe. No inflation required, no special initial conditions, just the natural evolution of spacetime through quantum bounces. Another problem cyclic cosmology solves is the flatness problem. Observations show that the universe is spatially flat, meaning that parallel lines remain parallel over cosmic distances. But in standard cosmology, flatness is unstable. Any slight deviation from perfect flatness in the early universe would have been amplified over time, and the universe should be either strongly curved or strongly hyperbolic by now. The fact that it's flat requires incredibly fine-tuned initial conditions. Inflation solves this by stretching the universe so much that any initial curvature becomes negligible. But cyclic cosmology solves it differently. If the universe goes through repeated cycles of collapse and bounce, each cycle naturally drives the universe toward flatness. Curvature gets smoothed out over multiple cycles, and flatness emerges as the stable equilibrium state. These are elegant solutions, but they come with a cost. Cyclic cosmology requires that information survives the quantum bounce, that the properties of the previous universe are somehow encoded in the structure of the new universe. This seems to violate the second law of thermodynamics, which says that information is lost as entropy increases. But recent work in quantum information theory suggests that information might not be lost after all. It might be scrambled. This scrambling is so thorough that it would take longer than the age of the universe to decode the information. But, in principle, it's still there. If this is true for black holes, it might also be true for white holes. The information about the previous universe might be encoded in the structure of the white hole, in the patterns of matter and energy it expels, waiting to be decoded by sufficiently advanced observers. This raises a fascinating possibility, that we might be able to read the history of the previous universe by studying the cosmic microwave background. If our universe emerged from a white hole, and if that white hole encoded information about the black hole it came from, then that information should be imprinted in the temperature fluctuations of the cosmic microwave background. It would be incredibly subtle, buried beneath layers of noise and cosmic evolution. And they give us something concrete to test. If future observations confirm these anomalies and reveal additional patterns that match the predictions of cyclic cosmology, it would be strong evidence that white holes are real and that our universe is part of an eternal cycle of bounces. But there's an even more radical possibility, one that pushes the boundaries of physics into territory that sounds like science fiction, but is grounded in rigorous mathematics. What if white holes aren't just the time-reversed versions of black holes? What if they're portals to other dimensions? This idea comes from string theory, the framework that attempts to unify quantum mechanics and general relativity by proposing that the fundamental constituents of reality are not particles, but tiny vibrating strings. String theory requires extra dimensions beyond the 3 spatial dimensions and 1 time dimension we experience. The most common version requires 10 dimensions total, 9 spatial and 1 temporal. The extra 6 spatial dimensions are compactified, curled up so small that we can't detect them directly. But they're there, and they affect the behavior of strings and the forces they produce. In string theory, black holes are not singularities. They're extended objects, strings and branes wrapped around the compactified dimensions. And the mathematics of string theory allows for solutions where black holes in our 4-dimensional spacetime are connected to white holes in higher dimensional spaces. Matter falling into a black hole doesn't just disappear. It travels through the extra dimensions and emerges from a white hole in a different region of the higher dimensional space. This is speculative, but it's based on solid calculations. In 2015, physicist Samir Mathur at Ohio State University showed that in string theory, the interior of a black hole is actually a highly excited state of strings, a fuzzball that extends throughout the extra dimensions. Information falling into the black hole gets encoded in the quantum state of this fuzzball, and when the black hole evaporates, the information is released through Hawking radiation. But Mathur's calculations also showed that the fuzzball can undergo transitions, quantum jumps, where it changes from a black hole configuration to a white hole configuration. These transitions happen in the extra dimensions, invisible to us, but they have observable consequences in our 4-dimensional spacetime. One consequence is that white holes in string theory should emit particles with specific properties, determined by the geometry of the extra dimensions. These particles would have masses and charges that reflect the compactification scale, the size of the curled-up dimensions. Detecting such particles would be direct evidence of extra dimensions and would confirm that white holes are portals to higher dimensional spaces. No such particles have been detected yet. The Large Hadron Collider at CERN has been searching for signs of extra dimensions since 2008, colliding protons at energies high enough to potentially produce particles from the compactified dimensions. So far, nothing. But the LHC is being upgraded, and by 2030, it will reach energies high enough to probe compactification scales that are currently inaccessible. If extra dimensions exist, if white holes are portals to these dimensions, we might finally have direct evidence within the next decade. There's also a connection between white holes and the holographic principle, one of the most profound ideas to emerge from string theory. The holographic principle states that all the information contained in a volume of space can be encoded on the boundary of that volume, like a hologram encoding a 3-dimensional image on a 2-dimensional surface. This principle was first proposed by Gerard 't Hooft in 1993 and developed by Leonard Susskind in 1995, based on studies of black hole thermodynamics. The holographic principle suggests that our 3-dimensional universe might be a hologram, a projection from a 2-dimensional surface that exists at the boundary of space-time. This sounds bizarre, but it's supported by calculations in string theory and by the ADS/CFT correspondence, a mathematical duality discovered by Juan Maldacena in 1997 that relates gravity in a higher dimensional space to quantum field theory on its boundary. White holes fit naturally into this holographic picture. If black holes encode information on their event horizons, then white holes should decode information from their event horizons. The matter and energy expelled by a white hole would be the holographic projection of information encoded on the white hole's boundary. And if our universe emerged from a white hole, then everything we observe, every particle and field and force, is a holographic projection from the boundary of that primordial white hole. This has testable consequences. If the universe is a hologram, there should be a maximum amount of information that can be contained in any region of space, determined by the area of the region's boundary. This maximum is called the Bekenstein bound, and it's been confirmed for black holes. But if it applies to the universe as a whole, then there should be subtle correlations in the cosmic microwave background, patterns that reflect the holographic structure of space-time. Several research groups are searching for these patterns, analyzing the statistical properties of temperature fluctuations in the cosmic microwave background to see if they match the predictions of holographic cosmology. The results so far are inconclusive. The The cosmic microwave background is consistent with holographic predictions, but it's also consistent with non-holographic models. We need more data, more precise measurements to distinguish between the possibilities. The next generation of cosmic microwave background experiments, including the Simons Observatory in Chile and the CMBS-4 project in Antarctica, will provide this data. If the universe is a hologram, if we're living inside the projection from a white hole's event horizon, we should know within the next 15 years. But perhaps the most profound implication of white holes is what they tell us about the nature of reality itself. They force us to confront the possibility that the universe is not a single objective reality, but a network of interconnected realities, each one emerging from quantum bounces and wormholes, each one with its own laws and constants and arrow of time. This is the multiverse, not as a speculative idea, but as a mathematical consequence of quantum gravity. In this picture, every black hole is a seed for a new universe. Matter falls in, undergoes a quantum bounce, and emerges as a white hole in a new spacetime. That new spacetime expands, forms galaxies and stars, and eventually produces new black holes, which seed new universes in turn. The process is eternal, a cosmic tree branching endlessly, with each branch representing a different universe, a different set of physical laws, a different history. We can't observe these other universes directly. They're causally disconnected from ours, separated by event horizons that nothing can cross. But we might be able to detect their influence indirectly, through subtle effects on the cosmic microwave background, or through gravitational waves from colliding white holes. And if we can detect these effects, if we can confirm that the multiverse is real, it would be the most revolutionary discovery in the history of science. It would mean that our universe is not unique, that reality is far vaster and stranger than we ever imagined, and that the questions we've been asking about the origin and fate of the universe are just the beginning of a much deeper inquiry into the nature of existence itself. White holes are not just exotic objects predicted by equations. They're windows into this deeper reality, glimpses of a cosmos where time is not absolute, where space is not continuous, where the boundaries between universes are permeable, and the distinction between past and future is an illusion created by our limited perspective. Finding them, understanding them, would not just answer questions about black holes or quantum gravity. It would transform our understanding of what it means to exist in a universe at all. I understand perfectly what you're thinking right now. This sounds like science fiction. White holes as portals to other universes. The Big Bang as a quantum bounce. Our reality as a hologram projected from a higher dimensional boundary. It sounds like the kind of speculation you'd find in a late-night documentary that plays fast and loose with the facts, mixing real physics with wild conjecture until you can't tell where science ends and fantasy begins. And I want to be completely honest with you. You're right to be skeptical. Because here's the uncomfortable truth that physicists don't always admit. We don't know if white holes are real. We have equations that predict them. We have theories that require them. We have observations that might be explained by them. But we don't have proof. Not yet. This is the edge of knowledge. The place where mathematics meets reality, and we're not sure which side we're standing on. Let me show you exactly how uncertain this all is. In 2023, physicist Sabine Hossenfelder at the Frankfurt Institute for Advanced Studies published a paper with a provocative title, White Holes, a Solution in Search of a Problem. Her argument was surgical and devastating. She pointed out that every observation we attribute to white holes, fast radio bursts, cosmic voids, anomalies in the cosmic microwave background, can be explained by conventional astrophysics. Fast radio bursts? Magnetars undergoing crustal rearrangements. Cosmic voids? Standard structure formation with slight variations in dark energy. Anomalies in the cosmic microwave background? Statistical fluctuations that inevitably appear when you analyze enough data. You don't need white holes to explain any of it. And in science, when you have two explanations for the same phenomenon, one requiring exotic new physics and one using established physics, you choose the established physics. It's called Occam's razor. The simplest explanation is usually correct. Hossenfelder went further. She argued that white holes might be mathematically possible, but physically forbidden. Just because an equation has a solution doesn't mean that solution corresponds to anything real. The equations of classical mechanics allow for a ball to spontaneously leap off the ground and fly upward, converting thermal energy into kinetic energy. It's mathematically valid. Every law of physics at the microscopic level is satisfied. But it never happens because the statistical probability is so close to zero that you could wait trillions of times the age of the universe and never see it. White holes might be the same, mathematically allowed but statistically impossible, solutions that exist on paper but nowhere in the actual cosmos. This criticism cuts deep because it's not coming from someone outside physics. Hossenfelder is a respected quantum gravity researcher who has spent decades working on the same problems as the physicists proposing white holes. She knows the mathematics. She understands the theories. And she's saying, we might be fooling ourselves. We might be so enamored with the elegance of the equations that we're ignoring the fact that nature doesn't care about elegance. Nature cares about what actually happens. And what actually happens might be that black holes simply evaporate through Hawking radiation, slowly and quietly, over timescales so long that the universe will be cold and dark before any of them finish. No quantum bounces, no white holes, no baby universes, just entropy increasing, information scrambling, and the inexorable march toward thermal equilibrium. But here's where it gets interesting. Because Hossenfelder's criticism, as sharp as it is, makes an assumption. It assumes that the laws of physics as we currently understand them are complete. That quantum mechanics and general relativity, properly unified, will give us a final theory that explains everything. And this assumption might be wrong. Consider what happened in the early 20th century. Physicists had two beautiful, complete theories: classical mechanics and classical electromagnetism. Both had been tested to extraordinary precision. Both made predictions that matched observations to many decimal places. And both were fundamentally wrong. Not wrong in the sense that they gave incorrect answers, they still work perfectly well for everyday phenomena, but wrong in the sense that they were incomplete, approximations to deeper theories that revealed themselves only when you pushed into extreme regimes. Quantum mechanics emerged when physicists studied atoms. Relativity emerged when they studied high velocities and strong gravity. The classical theories didn't predict these new frameworks. They couldn't. The new physics was hidden in regimes the old theories couldn't access. We might be in exactly the same situation now. Quantum mechanics and general relativity work beautifully in their respective domains. But when you try to combine them, when you push into the regime where both quantum effects and gravitational effects are important, the theories break down. They give infinities. They give paradoxes. They give predictions that don't make sense. And this breakdown might be telling us that we're missing something fundamental, some deeper layer of reality that we haven't discovered yet because we haven't been able to probe the right regime. White holes are predictions of this deeper layer. They emerge when you apply quantum mechanics to the interior of black holes, when you take seriously the idea that space-time has a quantum structure. If that quantum structure is real, then white holes should be real. If it's not, if space-time is fundamentally continuous all the way down, then white holes are mathematical ghosts. The question is, which is it? In 2025, a team led by Abhay Ashtekar at Pennsylvania State University published results that might tip the scales. They had been running simulations of black hole interiors using loop quantum gravity, and they found something unexpected. The quantum bounce that transforms a black hole into a white hole produces a specific signature in the gravitational waves emitted during the transition. The signature is subtle, a particular pattern of frequency modulation that lasts only a few milliseconds, but it's distinctive. It can't be produced by any classical process. If you detect this signature, you've detected quantum gravity. You've proven that space-time has a discrete structure, and you've proven that white holes are real. The signature hasn't been detected yet, but the Einstein telescope, scheduled to begin operations in 2035, will be sensitive enough to detect it if it exists. The telescope will monitor the entire sky continuously, searching for gravitational waves from every possible source. If black holes are undergoing quantum bounces anywhere in the observable universe, if they're transforming into white holes and emitting these quantum signatures, the Einstein telescope will find them. We have 10 years to wait. 10 years to find out if white holes are real or if they're mathematical phantoms. But let's assume for a moment that white holes are real. Let's assume the Einstein telescope detects the quantum signature, confirms that black holes undergo bounces, proves that space-time is discrete. What then? What does it mean for our understanding of the universe? It means that the Big Bang was not the beginning. This is the most profound implication, the one that rewrites cosmology from the ground up. If black holes bounce into white holes, and if the Big Bang has the same mathematical structure as a white hole, then the Big Bang was a bounce. Our universe emerged from a previous universe that collapsed into a black hole, underwent a quantum transition, and exploded outward as a white hole. Everything we see, galaxies, stars, planets, life, is the aftermath of that explosion, the debris field of a cosmic bounce that happened 13.8 billion years ago. This solves the singularity problem. In standard Big Bang cosmology, if you run the clock backwards, the universe contracts to a point of infinite density and infinite temperature, a singularity, where the laws of physics break down. Physicists have always been uncomfortable with this. Infinities in physics usually signal that your theory is incomplete, that you're extrapolating beyond its domain of validity. The singularity at the Big Bang is exactly this kind of infinity. It's telling us that general relativity, which works perfectly well to describe the expanding universe, breaks down when you try to describe the moment of creation itself. But if the Big Bang was a quantum bounce, there's no singularity. The universe contracts to a minimum size, about 10 to the power of minus 99 cubic meters, where quantum effects halt the collapse and reverse it. The density is enormous, 10 to the power of 96 kilograms per cubic meter, the Planck density, but it's finite. The temperature is extreme, 10 to the power of 32 Kelvin, the Planck temperature, but it's finite. The laws of physics don't break down. They just transition from the classical regime, where general relativity dominates, to the quantum regime, where loop quantum gravity takes over. And in that quantum regime, the bounce is inevitable. It's not a special event that requires fine-tuning or miraculous initial conditions. It's a generic feature of quantum spacetime, something that happens whenever matter is compressed beyond the Planck density. This also solves the horizon problem in a different way than inflation. Remember, the horizon problem is that different regions of the universe that are now separated by vast distances have almost exactly the same temperature, even though they were never in causal contact in standard Big Bang cosmology. Inflation solves this by proposing that the universe underwent a period of exponential expansion that stretched a tiny, causally connected region to cosmic scales. But inflation requires special initial conditions, a particular configuration of quantum fields that's hard to explain. The bounce scenario offers an alternative. If our universe emerged from a black hole in a previous universe, then the uniformity of the cosmic microwave background is explained by the uniformity of the matter that fell into that black hole. Black holes are extraordinarily efficient mixers. Matter falling in from different directions, with different compositions and temperatures, gets thoroughly mixed and homogenized by the extreme tidal forces near the event horizon. By the time the matter reaches the center and undergoes the quantum bounce, it's been mixed so thoroughly that all memory of its original configuration is erased. The bounce produces a uniform, homogeneous universe, not because of inflation, but because the black hole mixed everything together before the bounce. This is testable. If the Big Bang was a bounce, there should be subtle signatures in the cosmic microwave background that differ from the signatures predicted by inflation. Inflation predicts a specific pattern of temperature fluctuations, a nearly scale-invariant spectrum with a slight tilt. The bounce scenario predicts a different pattern, with additional features at large angular scales that reflect the quantum geometry of the bounce. Several research groups are analyzing cosmic microwave background data to search for these features. The Planck satellite found hints of anomalies at large scales, a deficit of correlations that doesn't quite match inflation predictions, but the statistical significance is marginal. The next generation of experiments, including the Simons Observatory and CMBS-4, will have the sensitivity to confirm or rule out these anomalies. If they're real, if they match the bounce predictions, it would be strong evidence that our universe came from a white hole. But there's a deeper question lurking here, one that goes beyond cosmology and touches on the nature of existence itself. If our universe came from a white hole, and if that white hole was the quantum bounce of a black hole in a previous universe, then where did that previous universe come from? Did it also come from a white hole, and the universe before that? Is it white holes all the way down? This is the eternal universe scenario, and it's both elegant and unsettling. Elegant because it eliminates the need for a beginning, for a moment of creation that requires explanation. The universe has always existed, cycling through phases of expansion and contraction, black holes and white holes, with no first cause and no final end. Unsettling because it challenges our intuition about time and causality. We're used to thinking of time as having a direction, an arrow that points from past to future. But in an eternal universe, that arrow is local, not global. Each cycle has its own arrow, pointing away from its white hole origin and toward its black hole future. But the cycles themselves have no overall direction. They just are, existing in a timeless network of quantum bounces. This raises a philosophical question that physics alone can't answer. If the universe is eternal, if it has no beginning, does it need a cause? The traditional argument for a creator is that everything that begins to exist must have a cause. And since the universe began to exist at the Big Bang, it must have a cause. But if the universe didn't begin, if it's eternal, then this argument collapses. The universe doesn't need a cause because it never came into existence. It's always been here, cycling through different forms, with each cycle emerging from the quantum bounce of the previous one. Some physicists find this deeply satisfying. It removes the mystery of creation, replacing it with an eternal process governed by physical laws. Others find it deeply unsatisfying. It pushes the mystery back, but doesn't eliminate it. Instead of asking, why is there something rather than nothing, we're now asking, quote, 14. The question changes form, but doesn't go away. And there's another complication. If the universe is eternal, if it's been cycling through black holes and white holes forever, then why isn't it in thermal equilibrium? The second law of thermodynamics says that entropy always increases. In an eternal universe, entropy should have increased to its maximum value an infinite time ago. The universe should be in a state of maximum disorder, with no structure, no galaxies, no stars, no life. Just a uniform sea of thermal radiation at the same temperature everywhere. This is called the heat death, and it's the inevitable fate of any closed system given enough time. But we don't live in a heat death universe. We live in a universe with structure, with galaxies and stars and planets, with vast differences in temperature and density. This suggests that either the universe is not eternal, or entropy doesn't always increase, or there's some mechanism that resets entropy at each bounce. The third option is what most physicists working on cyclic cosmology favor. They propose that the quantum bounce doesn't just reverse the collapse, it also resets entropy, creating a new universe with low entropy initial conditions. The mechanism is controversial. Some argue that quantum effects at the Planck scale naturally produce low entropy states. Others argue that information is lost during the bounce, and the loss of information corresponds to a decrease in entropy. Still others argue that entropy is not a fundamental quantity, but an emergent property that depends on how you coarse-grain the system, and that what looks like low entropy from one perspective might be high entropy from another. None of these arguments is fully convincing. The entropy problem remains one of the biggest challenges for cyclic cosmology. And it's a challenge that white holes make worse, not better. Because white holes, by their very nature, seem to decrease entropy. They take a high entropy state, matter compressed to extreme density inside a black hole, and transform it into a low entropy state, matter expanding outward in an ordered fashion. This appears to violate the second law of thermodynamics, and no amount of mathematical sophistication has fully resolved this paradox. In 2024, physicist Sean Carroll at Johns Hopkins University published a paper arguing that the entropy problem might be a sign that we're thinking about white holes in the wrong way. Carroll pointed out that entropy is not an objective property of a system. It's a measure of our ignorance about the system's microstate. A high entropy state is one where many different microstates correspond to the same macrostate, so we have a lot of uncertainty about which microstate the system is actually in. A low entropy state is one where only a few microstates correspond to the macrostate, so we have less uncertainty. From this perspective, white holes don't decrease entropy, they reveal information. When a black hole bounces into a white hole, the information that was hidden inside the black hole becomes accessible again. The entropy appears to decrease because we're gaining information about the system's microstate. But the total entropy of the universe, including the information we don't have access to, might still be increasing. This is subtle, and it's controversial. Many physicists argue that Carroll is playing word games, redefining entropy in a way that makes the problem disappear without actually solving it. But others argue that he's onto something deep, that the entropy problem is really a problem about information and observation, not about thermodynamics per se. The debate continues, and it's unlikely to be resolved without a complete theory of quantum gravity that tells us exactly how information behaves in extreme gravitational fields. But let's step back from the technical details and ask a broader question. What would it mean if white holes are real? Not just for physics, but for our understanding of reality itself. It would mean that the universe is far more dynamic than we thought. We're used to thinking of space-time as a stage on which events unfold, a fixed background that doesn't change. But if white holes are real, space-time is not a stage, it's an actor. It has its own dynamics, its own quantum properties, its own ability to transform and evolve. Black holes don't just warp space-time, they change its topology, creating new regions that didn't exist before. White holes don't just expel matter, they create new space-time, new regions of the universe that emerge from quantum bounces. This is a radically different picture of reality. In this picture, the universe is not a single, continuous space-time that began at the Big Bang and will end in heat death. Selected not by design, but by the random quantum fluctuations that determine which black holes bounce into which white holes. Some physicists find this idea liberating. It explains why the constants of nature seem fine-tuned for life. They're not fine-tuned. We just happen to live in one of the universes where the constants allow for complexity and structure and observers. In other universes, the constants are different, and those universes are sterile, devoid of life. We don't observe those universes because we can't exist in them. This is the anthropic principle, and it's controversial, but it's a logical consequence of the multiverse. Others find the multiverse idea deeply troubling. If there are infinitely many universes with infinitely many different laws of physics, then physics loses its predictive power. You can't predict what will happen in an experiment because anything that can happen does happen somewhere in the multiverse. The best you can do is calculate probabilities. And even those probabilities depend on how you count universes, which is ambiguous. This is called the measure problem, and it's one of the biggest challenges facing multiverse theories. But here's what's remarkable. We might be able to test the multiverse hypothesis. If our universe emerged from a white hole, and if that white hole was connected to a black hole in another universe, then there might be subtle correlations between our universe and that other universe. These correlations would show up as patterns in the cosmic microwave background, anomalies that can't be explained by processes within our universe alone. Several research groups are searching for these patterns, looking for what they call bubble collisions, places where our universe might have collided with another universe in the early stages of expansion. The search has been going on for over a decade, and so far, nothing definitive has been found. The cosmic microwave background is remarkably smooth, matching the predictions of standard inflation to extraordinary precision. But there are those persistent anomalies: the cold spot, the hemispherical asymmetry, the deficit of large-scale correlations. These could be statistical flukes, or they could be the first hints of other universes, the first evidence that we're part of a vast multiverse connected by white holes. We're living in a unique moment in the history of science. For the first time, we have the mathematical tools to describe quantum gravity, the observational tools to test its predictions, and the computational tools to simulate its dynamics. White holes are no longer just mathematical curiosities. They're testable hypotheses, predictions that will be confirmed or ruled out within the next 2 decades. The Einstein telescope will search for quantum signatures in gravitational waves. The Square Kilometre Array will search for white hole explosions in fast radio bursts. The next generation of cosmic microwave background experiments will search for anomalies that might reveal our white hole origin. And if we find evidence, if we detect the quantum signature, if we observe a white hole explosion, if we confirm the anomalies in the cosmic microwave background, it will be one of the greatest discoveries in human history. It will tell us that space-time is quantum, that the universe is eternal, that reality is a multiverse of interconnected bubbles, and that the Big Bang was not a beginning, but a transformation. It will rewrite cosmology, revolutionize our understanding of time and causality. Where mathematics meets reality, we don't know which side we're standing on. We don't know if white holes are real or imaginary, if the multiverse exists or if we're alone, if time is fundamental or emergent, if the universe had a beginning or has always existed. We don't know. And that's what makes this the most exciting time in physics since the quantum revolution of the 1920s. We're on the verge of discovering something profound about the nature of reality. We just don't know yet what it is. There's a photograph that hangs in the office of Carlo Rovelli at Aix-Marseille University. It's not a famous image. You won't find it in textbooks or museums. It shows a simple mirror, tilted at an angle, reflecting a window that opens onto a garden. But Rovelli keeps it there, as a reminder of something he wrote in 2018. A white hole is not the opposite of a black hole. It's a mirror. And what we see in that mirror is ourselves, looking back from the other side of time. This is where we need to go now. Not deeper into the mathematics, not further into the observations, but outward, into the philosophical territory where physics meets the fundamental questions about existence. Because white holes, whether they're real or mathematical phantoms, force us to confront something we've been avoiding throughout this entire journey: the nature of time itself. We've talked about time as if we understand it. We've described black holes pulling matter forward in time, white holes pushing matter backward in time, quantum bounces connecting past and future. But here's the uncomfortable truth. We don't actually know what time is. We can measure it. We can describe how it behaves in different gravitational fields. We can write equations that predict how it flows. But we cannot explain why it exists, why it has a direction, or why we experience it as a continuous flow from past to future, when the fundamental laws of physics treat past and future as interchangeable. This is called the problem of time, and it's been haunting physics since the Wheeler-DeWitt equation appeared in 1967. That equation, remember, describes the quantum state of the entire universe, and it contains no time variable. Time has vanished from the mathematics. What remains is a static description of all possible configurations of the universe, existing simultaneously in a timeless superposition. Time, in this view, is not fundamental. It's emergent, something that appears only when you divide the universe into parts and look at how one part evolves relative to another. White holes make this problem acute, because if time is emergent, if it arises from the relationships between parts of the universe rather than being woven into the fabric of reality itself, then the distinction between black holes and white holes might be an artifact of perspective. What you call a black hole depends on which direction you define as forward in time. Change your perspective, reverse your definition of temporal direction, and the black hole becomes a white hole. They're not different objects. They're the same object, viewed from opposite sides of the mirror. In 2026, physicist Marina Cortez at the University of Lisbon published a paper exploring this idea using a framework called the causal set approach to quantum gravity. In this framework, space-time is not a continuous fabric, but a discrete network of events, connected by causal relationships. An event can influence another event only if it's in that event's causal past. The network of these causal relationships defines the structure of space-time. And here's the key insight. The direction of time is defined by the direction of causality. Time flows from cause to effect. But causality, Cortez showed, is not absolute. It depends on the observer. Two observers moving relative to each other might disagree about which events are in the causal past of a given event, and which are in the causal future. This is already true in special relativity. It's called the relativity of simultaneity. But Cortez extended this to quantum gravity, showing that in a discrete spacetime, causality itself can be in superposition. An event can be simultaneously in the causal past and causal future of another event, depending on the quantum state of the spacetime network. Applied to black holes and white holes, this means that the same object can be both simultaneously. From one observer's perspective, matter is falling in, and it's a black hole. From another observer's perspective, matter is coming out, and it's a white hole. Both perspectives are equally valid. Both are describing the same physical object, just from different positions in the causal network. The object itself is neither black nor white. It's a quantum superposition of both, and which one you observe depends on how you're embedded in the causal structure of spacetime. This is not just philosophical speculation, it has observational consequences. If black holes and white holes are quantum superpositions, then there should be interference effects, quantum correlations between the matter falling in and the matter coming out. These correlations would be incredibly subtle, but they should be detectable in the Hawking radiation emitted by black holes. Several research groups are now developing theoretical frameworks to predict exactly what these correlations should look like and how we might detect them with future observations. But let's push this further. If time is emergent, if causality is relative, If black holes and white holes are perspectives rather than distinct objects, then what does this tell us about the nature of reality? It tells us that reality is not made of things, it's made of relationships. This is the core insight of relational quantum mechanics, a framework developed by Carlo Rovelli in the 1990s. In this view, properties don't belong to objects in isolation, they belong to interactions between objects. An electron doesn't have a definite position until it interacts with something that measures its position. A photon doesn't have a definite polarization until it interacts with something that measures its polarization. And a region of spacetime doesn't have a definite causal structure until it interacts with an observer who defines what past and future mean. White holes fit naturally into this relational picture. They're not objects that exist independently, waiting to be discovered. They're relationships, patterns of interaction between matter and spacetime that manifest differently depending on the observer's perspective. From the perspective of matter inside a collapsing black hole, the quantum bounce is a white hole, a moment when the collapse reverses and matter begins expanding outward. From the perspective of an observer outside the black hole, the same event might appear as Hawking radiation, a slow evaporation that takes billions of years. Both descriptions are correct. Both are describing the same physical process, just from different relational perspectives. This has profound implications for the question we started with. Are white holes real? The answer is, it depends on what you mean by quote 20. If you mean quote 21, then the answer might be no. But if you mean quote 22, then the answer is yes. White holes are real in the same way that temperature is real. Temperature doesn't exist as a property of individual atoms. It emerges from the collective behavior of many atoms, and it depends on how you coarse-grain the system, how you divide it into macroscopic parts. But temperature is still real. It has measurable effects. It determines whether water freezes or boils, whether stars shine or collapse. White holes might be real in exactly this sense, emergent features of quantum spacetime that depend on perspective but have genuine physical consequences. Now consider what this means for the Big Bang. If our universe emerged from a white hole, and if white holes are relational rather than absolute, then the Big Bang itself is relational. It's not an objective event that happened 13.8 billion years ago. It's a description of how our region of spacetime relates to other regions, how the causal structure of the universe appears from our particular perspective within it. From another perspective, perhaps from the perspective of the parent universe whose black hole bounced into our white hole, the Big Bang might appear completely different. It might appear as a black hole evaporating, or as a quantum fluctuation in a larger spacetime, or as something we don't have words for because we're trapped in our own relational perspective. This is dizzying. It challenges everything we think we know about cosmology, about the origin of the universe, about the nature of existence itself. But it's where the mathematics leads us. And it's where white holes, these strange mirror images of black holes, force us to go. There's another layer to this, one that connects to consciousness and observation in ways that make physicists deeply uncomfortable. If reality is relational, if properties emerge from interactions rather than existing independently, then observers play a fundamental role in defining what exists. This sounds like mysticism, like the kind of quantum woo that serious physicists spend their careers debunking. But it's not mysticism. It's a direct consequence of taking quantum mechanics seriously. In quantum mechanics, the act of measurement doesn't just reveal pre-existing properties, it creates them. Before you measure an electron's position, it doesn't have a definite position. It exists in a superposition of all possible positions. The measurement forces the electron to choose one position, to collapse from superposition into a definite state. This is not controversial. It's been confirmed by thousands of experiments over the past century. What's controversial is what this means for reality. The standard interpretation, called the Copenhagen interpretation, says that quantum mechanics is just a tool for predicting measurement outcomes. It doesn't describe reality itself, only our knowledge of reality. But this interpretation has a problem. It requires a sharp boundary between the quantum world, where superpositions exist, and the classical world, where measurements happen. And nobody can say where that boundary is. Is it at the level of atoms, molecules, measuring devices, human consciousness? The boundary seems arbitrary, and this arbitrariness suggests that the Copenhagen interpretation is incomplete. Relational quantum mechanics offers a different answer. It says there is no boundary. Everything is quantum, including observers and measuring devices. But quantum properties are relational. They exist only in the context of interactions. An electron has a definite position relative to a measuring device that interacts with it, but it doesn't have a definite position relative to the rest of the universe. Different observers, interacting with the electron in different ways, might see different positions, and all of them are correct relative to their own perspective. Applied to white holes, this means that whether a region of spacetime is a black hole or a white hole might depend on the observer. Not in a subjective sense, not in the sense that you can choose to see it however you want, but in a physical sense. Different observers, embedded in different parts of the causal network, interacting with spacetime in different ways, might genuinely observe different causal structures. One observer sees matter falling in, another sees matter coming out. Both are correct. Both are describing real physical interactions. The white hole is real for the observer who interacts with it as a white hole, and the black hole is real for the observer who interacts with it as a black hole. This is not a comfortable conclusion. It suggests that reality is not a single objective structure that exists independently of observation. It's a network of overlapping perspectives, each one valid within its own context, each one describing genuine physical relationships, but none of them capturing the totality of what exists. We're used to thinking of physics as revealing the objective truth about the universe, the way things really are beneath the appearances. But quantum gravity, and white holes in particular, suggest that there might not be a single objective truth. There might only be perspectives, relationships, interactions, each one revealing a different facet of a reality that's too complex to be captured by any single description. Some physicists find this liberating. It means that the universe is richer than we thought, that there are multiple valid ways of describing it, multiple layers of reality that coexist without contradicting each other. Others find it deeply troubling. It seems to undermine the entire project of physics, which is to find universal laws that apply everywhere and always, regardless of perspective. If reality is relational, if different observers see different things, then what are the laws of physics laws of? What is it that remains constant across all perspectives? The answer might be the relationships themselves. The laws of physics don't describe objects. They describe how objects interact, how they relate to each other, how information flows between them. And these relationships might be universal, even if the objects themselves are perspective-dependent. A black hole and a white hole might be different perspectives on the same object, but the relationship between them, the quantum bounce that connects them, the causal structure that defines their interaction, might be the same for all observers. The laws of quantum gravity would then be laws about these relationships, about how space-time interacts with itself, about how causal structures emerge and evolve. This is speculative, but it's grounded in serious physics, and it points toward a new way of thinking about reality, one where the fundamental constituents are not particles or fields, or even space-time itself, but relationships, interactions, patterns of information flow that persist across different perspectives. Now let's return to the question that's been lurking beneath this entire discussion. Why does the universe exist at all? Why is there something rather than nothing? This is the ultimate question, the one that physics alone cannot answer, because physics describes how things behave, not why they exist in the first place. But white holes, and the relational view of reality they suggest, might offer a hint. If reality is made of relationships, then existence is not a property of individual objects, it's a property of networks. An object exists insofar as it's embedded in a network of relationships with other objects. An electron exists because it interacts with photons and other electrons and the electromagnetic field. A galaxy exists because it interacts with other galaxies through gravity. The universe exists because its parts interact with each other, forming a vast network of causal relationships that we call space-time. But here's the key insight. This network doesn't need a foundation. It doesn't need to rest on anything more fundamental. It's self-supporting, like a spider's web that hangs in space without being attached to anything. Each strand supports the others, and the web as a whole exists because of the relationships between the strands, not because it's anchored to some external structure. White holes fit into this picture as nodes in the network, junctions where causal relationships converge and diverge. A black hole is a node where causal paths flow inward. A white hole is a node where causal paths flow outward. The quantum bounce that connects them is a transformation of the network structure, a moment where the pattern of relationships changes. And the universe as a whole is the sum of all these nodes and transformations, a self-sustaining network of causal relationships that exists not because something created it, but because the relationships themselves are self-consistent. This doesn't answer the question, quote, 24, but it reframes it. Instead of asking why the universe exists, we should ask why this particular network of relationships exists, rather than some other network, or no network at all. And the answer might be because this network is self-consistent. It's a stable pattern of relationships that can sustain itself without external support. Other networks might be possible in principle, but they're unstable or inconsistent or unable to support the kind of complex structures that give rise to observers who can ask questions about existence. This is the anthropic principle again, but in a deeper form. We exist in this universe, with these laws of physics and these constants of nature, not because it was designed for us, but because this is the kind of universe that can support observers. Other universes, other networks of relationships, might exist in some abstract sense, but we can't observe them because we can't exist in them. The universe we observe is selected not by design, but by the requirement that it be capable of producing observers. White holes play a crucial role in this selection process. If black holes bounce into white holes, and if each white hole seeds a new universe with slightly different laws of physics, then the multiverse is not a static collection of universes. It's an evolving network, with new universes constantly being born from old ones, each one inheriting properties from its parent, but with quantum variations. Over countless cycles, this process would naturally select for universes that are stable, that can support complex structures, that can produce black holes, which seed new universes. We live in one of these selected universes, one that's been refined over countless generations of cosmic evolution. This is speculative, but it's testable in principle. If our universe was born from a white hole, and if that white hole inherited properties from a parent universe, then there should be correlations between the properties of our universe and the properties of the parent. These correlations would show up as patterns in the cosmic microwave background, as relationships between the constants of nature that can't be explained by processes within our universe alone. We're not yet at the point where we can detect these patterns, but we're getting closer. The next generation of cosmological observations might reveal the fingerprints of the parent universe, the first evidence that we're part of a vast cosmic genealogy stretching back through countless cycles of black holes and white holes. But let's be honest about the limits of what we know. We've traveled far in this exploration, from the mathematics of general relativity to the quantum structure of space-time, from the search for observational evidence to the philosophical implications of relational reality. And at every step, we've encountered uncertainty. We don't know if white holes are real. We don't know if the Big Bang was a quantum bounce. We don't know if the universe is eternal or if it had a beginning. We don't know if time is fundamental or emergent. We don't know if reality is objective or relational. We don't know if we're alone in a single universe or part of a vast multiverse. What we do know is this: the mathematics of our best theories predicts white holes. The equations of general relativity, combined with quantum mechanics, naturally produce solutions where black holes bounce into white holes. These solutions are not arbitrary. They emerge from the fundamental requirement that space-time have a quantum structure, that there be a minimum scale below which space and time cannot be divided. And if space-time is quantum, if it's made of discrete building blocks rather than being continuous, then white holes should exist. The question is not whether the mathematics allows them, but whether nature implements them. And we're on the verge of finding out. Within the next 10 to 20 years, we'll have observational tools sensitive enough to detect the signatures of white holes if they exist. The Einstein telescope will search for quantum echoes in gravitational waves. The Square Kilometre Array will search for white hole explosions in fast radio bursts. The next generation of cosmic microwave background experiments will search for patterns that reveal our white hole origin. These are not distant dreams. These are funded projects, telescopes under construction, experiments that will begin taking data within the lifetime of anyone watching this video. We're living in the era when humanity will finally answer one of the deepest questions we've ever asked. What is the nature of space-time? Is it continuous or discrete? Is it fundamental or emergent? Does it have a quantum structure? And if so, what are the consequences? White holes are the key to answering these questions. They're the predictions that distinguish between different theories of quantum gravity, the observations that will tell us which framework is correct. And if we find them, if we detect the quantum signature of a black hole bouncing into a white hole, it will be more than just a confirmation of a theoretical prediction. It will be a revelation about the nature of reality itself. It will tell us that time is not what we thought it was, that causality is more subtle than we imagined, that the universe is part of a larger structure we're only beginning to glimpse. It will tell us that the Big Bang was not a beginning, but a transformation, that our universe emerged from something that came before, and that everything we see around us, galaxies, stars, planets, life, consciousness, is the aftermath of a cosmic bounce that happened 13.8 billion years ago. But if we don't find them, if the observations come back negative, if white holes turn out to be mathematical ghosts with no physical reality, that will also be a revelation. It will tell us that space-time is not quantum in the way we thought, that the discrete structure predicted by loop quantum gravity doesn't exist, that we need a different framework to unify quantum mechanics and general relativity. It will send us back to the drawing board, searching for new theories, new mathematics, new ways of understanding the fabric of reality. Either way, we'll learn something profound. Either way, we'll take a step closer to understanding what the universe is, how it works, and why it exists. This is the edge of knowledge, the frontier where human understanding meets the deepest mysteries of existence. And white holes, these strange mirror images of black holes, these time-reversed regions that might or might not exist, are our guides into this unknown territory. Remember the photograph in Carlo Rovelli's office? The mirror reflecting the window onto the garden? White holes are that mirror. They show us ourselves, our theories, our assumptions about time and causality and reality reflected back from the other side. And what we see in that reflection might be beautiful, or it might be unsettling, or it might be something we don't yet have words for. But it will be true. It will be a glimpse of reality as it actually is, beneath the layers of interpretation and assumption and perspective that we've built up over centuries of scientific inquiry. We don't know what we'll find when we look into that mirror. We don't know if white holes are real or imaginary, if the universe is eternal or finite, if time is fundamental or emergent. We don't know if we're alone in a single cosmos or part of an infinite multiverse of branching realities. We don't know if consciousness plays a fundamental role in defining what exists, or if it's just an emergent property of complex information processing. We don't know if the questions we're asking are the right questions, or if we're missing something so fundamental that future generations will look back at our confusion with the same mixture of sympathy and amusement that we feel when we read about medieval debates over how many angels can dance on the head of a pin. But we're asking the questions. We're building the telescopes. We're running the simulations. We're doing the mathematics. We're pushing against the boundaries of knowledge, trying to see what lies beyond. And that, in itself, is remarkable. That a species of evolved primates on a small planet orbiting an ordinary star in an unremarkable galaxy can ask questions about the nature of space-time, about the origin of the universe, about the quantum structure of reality. That we can even formulate these questions, let alone begin to answer them, is perhaps the most extraordinary fact about the cosmos. White holes, whether they exist or not, remind us of this. They remind us that the universe is stranger than we imagine, that reality operates by rules we're still discovering, that the boundary between the known and the unknown is not a wall, but a horizon, constantly receding as we approach it. They remind us that we're part of something vast and ancient and mysterious, a cosmic process that's been unfolding for billions of years and will continue for billions more, with or without us. And they remind us that every answer we find opens up new questions, deeper mysteries, further horizons. If white holes are real, we'll ask, what determines when a black hole bounces? Can we predict it? Can we control it? Could an advanced civilization use white holes as portals to other universes, as engines for creating new realities? If white holes aren't real, we'll ask, why does the mathematics predict them? What are we missing? What deeper theory will finally explain why space-time behaves the way it does? The questions never end. The mystery never resolves. And that's not a failure of science, that's its greatest triumph. Because it means that reality is inexhaustible, that there's always more to discover, always deeper layers to explore, always new horizons to reach toward. We're not at the end of physics. We're at the beginning of a new chapter, one where quantum gravity and cosmology and the nature of time itself are finally within our grasp. White holes are the doorway to that chapter. They're the question mark at the edge of everything we know, the mirror reflecting mysteries we haven't yet learned to see. And whether they're real or imaginary, whether we find them or not, they've already changed how we think about the universe. They've shown us that reality is more flexible than we thought, that time is more subtle, that the boundaries between possible and impossible are not as clear as we assumed. So when you look up at the night sky, when you see the stars scattered across the darkness, remember, somewhere out there, perhaps, a black hole is undergoing a quantum bounce. Space-time is transforming, causality is reversing, and a white hole is being born. Matter that fell into darkness billions of years ago is exploding outward into light, seeding a new universe, creating new space-time, new possibilities, new futures. Or perhaps not. Perhaps white holes are just mathematical dreams, elegant solutions to equations that describe nothing real. Perhaps the universe is simpler than we thought, or stranger in ways we haven't imagined yet. We don't know. And that's the point. That's the beauty of it. That's why we keep searching, keep questioning, keep pushing against the boundaries of the known. Because somewhere out there, at the edge of everything, reality is waiting to surprise us. And white holes, these impossible objects that might or might not exist, are our invitation to discover what that surprise might be. The mirror is waiting. The question is, are we ready to look into it?